Hello, night travelers, those restless souls who seek calm within the quiet symphony of the night. Welcome back to the Night Observer, a place where minds grow lighter, worries soften, and sleep arrives gently, carried on thoughts of the vast and mysterious universe. The fire is lit once more. We gather again, drawn together by its warmth, listening as the universe tells its oldest stories. Tonight, we lift our eyes to the sky and let ourselves sink into the immensity above. What do you notice first? Yes, the stars. Like our sun, they have been present since humanity first became aware of its own existence. Take a slow, deep breath. Let your chest rise. Feel the weight of the day ease its grip. Imagine yourself resting in a small, quiet boat, drifting across a velvet black ocean of space, where the distant light of countless stars weaves an eternal tapestry. Tonight, we will not linger among rocky planets or gas giants. Instead, we will turn the clock back billions of years, slipping into the deepest stillness of the cosmos to witness one of creation's most profound moments, the birth of a star, the first whisper of light rising from darkness. There is no need to remember numbers or technical terms. Let your thoughts become as light as cosmic dust. Allow your breathing to slow as you listen to the story of how light itself is born, gently guiding you toward rest beneath the timeless glow of the stars. Giant cocoons, nebulae, and primordial matter. Every great beginning emerges from silence, and the birth of a star is no exception. The universe did not begin in brilliance, but in vast, frigid clouds of gas and dust drifting through interstellar space. These regions, known as nebulae or star nurseries, are composed primarily of hydrogen, the simplest and most abundant element in all of cosmic history. These nebulae, often called giant molecular clouds, can stretch hundreds of light years across and contain millions of times the mass of our sun. Though they appear soft and cloud-like, they are extraordinarily sparse, with densities of only a few thousand particles per cubic centimeter. And yet, within this delicate thinness lie all the ingredients needed to form solar systems, roughly 70% hydrogen, 28% helium, and trace amounts of heavier elements forged in earlier generations of stars. For millions of years, these clouds drift in near-perfect silence, chilled to temperatures barely above absolute zero. But deep within them, an unseen force quietly begins its work. Gravity. The dance of gravity. When darkness begins to contract, gravity is the universe's most patient architect. Slowly, it draws particles closer together. Under ordinary conditions, a molecular cloud can remain in balance, with the outward pressure of gas countering gravity's inward pull. But this balance is fragile. A disturbance, a shock wave from a nearby supernova, a collision between clouds, or the passage through a galaxy's spiral arm can break the stillness. When a region becomes dense enough to exceed what is known as the Jeans mass, gravity gains the upper hand. Collapse begins, and there is no turning back. The cloud does not fall inward as one body. Instead, it fragments into many smaller clumps, each becoming the seed of a future star. At the heart of these fragments form dense, opaque knots known as Bach globules, dark cocoons that conceal the birth of stars from visible light, yet reveal themselves softly in infrared glow. The protostar, heat born from motion. Within these cocoons, matter rushes inward under gravity's pull. As particles collide, their motion transforms into heat. The central region grows warmer and brighter, though it is not yet a true star. At this stage, it is known as a protostar. Like a child growing within the womb of the cosmos, the protostar feeds steadily from its surrounding disk of gas and dust. As it gathers mass, it spins faster, flattening the surrounding material into a broad, rotating disk, the birthplace of future planets. The protostar shines not from nuclear fire, but from the energy released by contraction. Temperatures rise from thousands to millions of degrees. Hydrogen molecules break apart into atoms, then into charged particles, forming a glowing plasma, a sea of restless energy. Here, a silent struggle unfolds. Gravity presses inward while heat begins to push back. One final transformation remains. Nuclear awakening, when light takes command. The defining moment arrives when the core temperature reaches roughly 10 to 18 million degrees Celsius. Under such extremes, hydrogen nuclei move fast enough to overcome their natural repulsion. Fusion begins. 4 hydrogen nuclei merge to form helium. In this union, a small fraction of mass, about 0.7%, is converted directly into energy, exactly as Einstein described in his quiet equation, E equals mc squared. That energy erupts outward as gamma radiation, beginning a long, arduous journey toward the surface, gradually softening into the warmth and light we recognize. At last, equilibrium is achieved. The outward pressure from fusion balances gravity's inward pull. The star stabilizes. Light reigns. A star is born. Mass is destiny, the lives of stars. The newborn star enters the long, steady phase of its life, spending most of its existence quietly burning hydrogen. Yet its fate is sealed by one defining trait: its mass. Massive blue giants blaze fiercely, consuming their fuel in mere millions of years before ending in spectacular supernovae. Small red dwarfs burn slowly and patiently, enduring for trillions of years, far longer than the universe has yet existed. Our sun rests between these extremes, a steady companion with a lifespan generous enough to allow life to flourish on a small blue world. Regardless of size, every star is an alchemical workshop. In their cores, they forge carbon, oxygen, nitrogen, the very elements that shape oceans, landscapes, and living beings. When stars die, they return these elements to space, where time and gravity gather them once more. And billions of years later, they form worlds capable of wondering where they came from. Now, as images of misty star nurseries, swirling seas of plasma, and the quiet miracle of fusion slowly fade from your mind, allow the night to settle completely around you. Feel the deep, unbroken peace of this moment. You are here, a wondrous being shaped from stardust itself, breathing air forged in the great nuclear furnaces of stars that burned billions of years ago. Every star above you is a silent witness to the long history of the universe, performing its ancient dance with dignity and restraint. Imagine yourself as a tiny ray of light, drifting gently back into the embrace of a velvety ocean of space, wrapped in the unseen warmth of a celestial halo. Let these distant whispers soothe the traveler's soul, guiding you softly toward rest beneath the eternal glow of the stars. Though they lie unimaginably far away, their ashes live on in every beat of your heart, binding you forever to the origin of all things. We have taken our first steps into the story of how stars are born, and now we continue. Welcome to Structure and Characteristics, the Symphony of Plasma. Prelude: Plasma, the state of the gods. In our small, familiar world, we grow up knowing 3 states of matter: solid, liquid, and gas. But beyond Earth, this understanding quietly dissolves. Out in the vastness of space, we are the exception. Nearly 99.9% of ordinary matter in the universe exists in a different form altogether: plasma. Stars, at their core, are nothing less than colossal spheres of this luminous state, held together by their own immense gravity. Plasma is often called the 4th state of matter. Imagine heating a block of ice. It melts into water, then evaporates into gas. But when energy continues to pour into that gas beyond ordinary limits, a remarkable transformation occurs. electrons break free from their atomic bonds, leaving behind a restless mixture of positively charged ions and free electrons, a living, dynamic sea of energy. The term plasma was introduced in 1928 by physicist Irving Langmuir, who saw in it a resemblance to blood plasma, carrying charged particles much as blood carries cells. Long before that, in 1816, Michael Faraday had sensed its existence and called it radiant matter, a name that feels almost prophetic in hindsight. The symphony of electrical and magnetic motion. What truly sets plasma apart from an ordinary gas is its extraordinary electrical nature. In a gas, particles remain mostly neutral, interacting only through direct collisions. In plasma, free charges move freely, responding instantly to electric and magnetic fields. Under many cosmic conditions, plasma behaves as though its conductivity were infinite. This gives rise to what scientists call collective behavior. Imagine a vast orchestra. Each charged particle is an individual musician, yet every movement is shaped by the invisible currents created by all the others. A single disturbance can ripple across the entire system, sending waves of motion through the star itself. Plasma also possesses an elegant balance known as quasi-neutrality. Though filled with charged particles, the overall positive and negative charges nearly cancel out when viewed on large scales. From a distance, the star appears calm and neutral. But deep within, on microscopic scales, electromagnetic tensions never rest, quietly fueling the star's vitality. Internal structure, shells of living light. Our sun offers a perfect example of how plasma arranges itself into layered harmony. Each region is a movement in an ongoing cosmic symphony. The core. At the very heart lies plasma in its most extreme state. Temperatures soar to nearly 15.7 million Kelvin, and matter is compressed to densities 150 times greater than water. Here, hydrogen nuclei are forced close enough to overcome their natural repulsion, merging through nuclear fusion. Every second, some 600 billion kilograms of hydrogen become helium, releasing vast energy as gamma radiation, the radiative zone. Surrounding the core is a dense plasma where light struggles to escape. Photons are absorbed and re-emitted countless times, wandering like travelers lost in a maze of mirrors. A single particle of light may take tens, or even hundreds, of thousands of years to find its way outward. The tachocline. This thin, hidden boundary is a region of transition. Here, the calm, uniform rotation of the inner layers meets the restless motion above. The resulting shear gives birth to the star's powerful magnetic fields, woven through the invisible machinery of the solar dynamo. The convective zone. Closer to the surface, plasma cools and begins to flow. Energy now rises and falls through enormous convective currents, like a slow, rolling boil. Hot plasma ascends, releases its heat, then sinks again, creating the mottled, granular patterns we observe on the sun's face. Plasma atmosphere, from surface to crown. As the symphony reaches the surface, plasma shapes the star's atmosphere into layers of increasing mystery. The photosphere. This is where plasma thins enough for light to escape freely into space. The surface we see with our eyes. The chromosphere. Above it lies a delicate, glowing layer, revealed only during total eclipses or through special instruments, shimmering briefly before fading again. The transition region. In this narrow boundary, temperatures leap suddenly from tens of thousands to millions of degrees, a mystery that continues to challenge our understanding. The corona. At the outermost edge, superheated plasma stretches millions of kilometers into space. Though unimaginably hot, it glows faintly, its matter spread thin like breath on cold air. And here, beneath this immense and silent architecture of light, you may rest, knowing that the same plasma that fuels the stars also gave rise to the atoms within you. Let that thought linger softly as the night carries you onward, deeper into stillness. Plasma and magnetic scars. When electrically conductive plasma meets magnetic fields, a star reveals its most restless and dramatic nature. Sunspots are born in these encounters, regions where magnetic fields grow so intense that they suppress the upward flow of heat from within. Deprived of warmth, the plasma cools, darkening these areas like ancient scars on the sun's glowing surface. At times, the motion of plasma twists magnetic field lines beyond their limits. When the tension becomes too great, those invisible lines snap and reconnect in a sudden release known as magnetic reconnection. In that instant, enormous torrents of plasma are hurled into space as solar flares or coronal mass ejections. No longer bound to the star, this charged matter streams outward as solar wind, filling the vast spaces between planets with a thin, restless, electromagnetic breath. Night travelers, we have listened to the birth of stars and traced the hidden forces that shape their light. Now, by the gentle warmth of this fire, let us hear an epic poem written across the cosmos. Mass, age, and scale, destiny written in weight. There is no need to remember numbers or technical terms. Let your thoughts grow light, like drifting cosmic dust. Allow your breathing to slow as the story of stellar life unfolds, softly guiding you toward rest beneath the eternal glow of the stars. Mass, the hands of destiny. In the universe, mass is destiny. From the moment a star gathers itself within a cold molecular cloud, its fate is already inscribed. Color, brightness, temperament, and even the manner of its death are all determined by how much matter it possesses. The threshold of existence. For a star to truly awaken, it must gather enough mass to ignite a stable fusion fire. That lower limit lies at about 8% of the Sun's mass, roughly 80 times the mass of Jupiter. Below this threshold, gravity is too weak to spark sustained hydrogen fusion. The result is a brown dwarf, a cosmic ember forever hovering between planet and star, never fully alive with light. Yet the universe also imposes limits on greatness. Some stars are born with more than 200 times the mass of the Sun. These giants are rare and deeply unstable. The radiation pouring from their cores presses outward with such force that it continuously strips away their outer layers, flinging matter back into space. The eternal struggle. Mass creates gravity, and gravity is both creator and destroyer. It relentlessly pulls inward, seeking collapse, while nuclear fusion pushes outward, fighting for balance. When these two forces meet in harmony, a star achieves hydrostatic equilibrium and shines steadily across billions of years. But greater mass means stronger gravity, and stronger gravity demands hotter, denser cores. The inevitable consequence is excess. The most massive stars are also the most extravagant, burning their fuel with breathtaking speed. Lifespan, the paradox of greatness. Here lies one of the universe's quiet ironies. The larger the star, the shorter its life. The youth-burning stars. Blue giants possess vast stores of hydrogen, yet they spend it recklessly. Their immense gravity drives fusion at a furious pace, consuming fuel millions of times faster than the Sun. As a result, the most massive stars may live only a few million years, an instant on cosmic scales. They blaze brilliantly, then perish in magnificent supernovae, scattering their elements across space. The timekeepers. At the opposite extreme are red dwarfs, the most common stars in the universe. Small, cool, and patient, they sip their fuel with extraordinary restraint. Their lifespans stretch into the trillions of years, far longer than the universe has existed so far. Every red dwarf ever born still shines quietly today, keeping watch through deep time. The middle path, our Sun. Our Sun walks a balanced course. With a total lifespan of roughly 10 billion years, it provides the long-term stability required for life to arise on Earth. Now in the calm middle age of its existence, It will one day expand into a red giant before shedding its outer layers and settling into quiet retirement as a white dwarf. Scale, palaces of light. The size of stars defies ordinary imagination. Scale reflects not only mass, but also where a star stands along its evolutionary path. From the smallest extremes. Neutron stars occupy one end of this vast range. Though more massive than the Sun, they are compressed into spheres only about 20 kilometers across, no larger than a city. Here, gravity has crushed atoms entirely. A single spoonful of their matter would weigh billions of tons. To the grandest titans. At the opposite extreme are supergiants and hypergiants, stars so immense they could engulf the entire solar system. Betelgeuse, the red beacon in Orion, spans roughly 640 to 764 times the Sun's radius. If placed at our Sun's position, it would swallow Mars and stretch nearly to the asteroid belt. Even larger still are UY Scuti and WOHG 64, with radii exceeding 1,700 times that of the Sun. Their size challenges our language. Light itself takes hours to travel around their equators. The fragility of immensity. Yet such greatness is delicate. These colossal stars are astonishingly diffuse, their outer layers thin and loosely bound. Surface gravity is weak, allowing matter to drift away continuously, forming vast envelopes of gas and dust. A quiet reminder that even the largest palaces of light are temporary. Each star above you is a witness to the universe's long memory, performing its silent dance with dignity and resolve. And now, imagine yourself as a tiny ray of light, drifting gently back into the velvety ocean of space, held in the invisible embrace of a stellar halo. Tonight on Night Travelers, we will move beyond observing individual spheres of glowing plasma. Together, we will step into a far grander epic, one that speaks of the forces that quietly built the world we inhabit. Welcome to the Architects of the Universe, their role in the Milky Way and beyond. The story of these architects begins in an age of profound stillness, when the universe itself lay wrapped in silence. Scientists call this era the Dark Ages. Roughly 380,000 years after the Big Bang, the primordial fog of charged particles settled. Space became transparent, the first light of recombination faded, and what remained was a cold, empty expanse where only hydrogen and helium drifted like ghosts in the dark. Yet even in that darkness, preparation was underway. Guided by gravity and the unseen scaffolding of dark matter halos, immense clouds of hydrogen gas began to contract. They compressed until the pressure became unbearable, giving birth to the very first stars, population 3 stars. These primordial suns were unlike anything we see today. Colossal, brilliant giants, hundreds of times more massive than our sun. When they ignited, they released the first true starlight, piercing the cosmic night and ushering in what we now call the cosmic dawn. But their purpose was far greater than illumination alone. These stars were the universe's first great alchemical furnaces. Before their birth, creation was simple and spare: light, hydrogen, and helium. Inside the searing hearts of stars, nuclear fusion transformed simplicity into richness. Hydrogen fused into helium, helium into carbon, carbon into nitrogen and oxygen, the essential elements of breath, bone, and blood. In the most massive stars, this process continued until iron was forged, the final step where fusion could give no more energy. When these architects reached the end of their brief yet magnificent lives, they offered one final, generous gift. They died in cataclysmic supernova explosions, scattering their carefully forged elements into the surrounding cosmos. In those violent moments, elements heavier than iron, gold, platinum, uranium, were created. Without these stellar deaths, the universe would remain little more than gas. Rocky worlds like Earth would never form, and neither would you. As physicist Lawrence Krauss once reflected, every atom in your body was once inside a star, or born from the earliest moments of the Big Bang. You are not merely in the universe, you are made of it. Turning our gaze inward toward our shared home, the Milky Way, we see how stars continue to shape destiny on a galactic scale. Our galaxy is not a fixed monument, but a living archive, built from the remnants of smaller galaxies drawn in by gravity over billions of years. Ancient stars in the galactic halo serve as silent witnesses, fossil light preserving the chemical fingerprints of the earliest universe. By studying these metal-poor stars, astronomers uncover the Milky Way's turbulent youth, shaped by collisions, mergers, and the invisible hand of dark matter. Within the graceful sweep of the spiral disk, younger stars take on the role of builders. The spiral arms are not rigid structures, but slow-moving density waves, gently compressing clouds of gas and dust. In these regions, stellar nurseries like the Orion Nebula and the Eagle Nebula come alive. New stars ignite by the millions, while powerful stellar winds and intense radiation from massive stars sculpt the surrounding clouds, carving pillars, hollowing cavities, and regulating the birth of future generations. Beyond shaping matter, stars quietly safeguard the possibility of life itself. Planetary systems are not rare accidents. They are a natural outcome of stellar formation. Around stable, long-lived stars like our Sun lies a delicate region known as the habitable zone, where warmth is gentle enough for liquid water to endure. Even humble red dwarf stars, the most numerous in the Milky Way, can serve as patient guardians, shining steadily for trillions of years, allowing life the time it needs to awaken. Now, night deepens. Images of blazing nuclear furnaces, of matter endlessly recycled through birth and death, begin to soften in your thoughts. You are here, safe on Earth, wrapped in an atmosphere sustained by a calm golden star. Feel the quiet, enduring connection between every cell in your body and the distant stellar explosions that occurred billions of years ago. Each star above you is a witness to the universe's long memory, performing its silent dance with dignity and resolve. And now, imagine yourself as a tiny ray of light, drifting gently into the embrace of the velvety black ocean of space, held by the invisible warmth of a stellar halo. The stars did not build this universe merely to exist, but to create a place where, one night, conscious beings could look upward and remember where they truly came from. Every great story in the universe begins in stillness, within darkness so deep it seems timeless. In that silence, giant molecular clouds drift through interstellar space like cold, wandering spirits. These vast regions, known as star nurseries, hold the most ancient materials of creation. Mostly hydrogen, a trace of helium, and fine dust forged in the depths of long-vanished stars. For millions of years, these clouds move without urgency, suspended in quiet balance. Then, almost imperceptibly, a gentle but relentless force awakens. Gravity, patient, tireless, begins to draw dust and gas closer together. Slowly, an irreversible spiral forms. When a portion of the cloud is compressed beyond its limit, it can no longer support its own weight. It collapses, breaking apart into thousands of dense fragments, each one a promise, a future sun waiting to be born. Within thick veils of dust, known to astronomers as Bok globules, matter falls inward freely. Motion becomes heat. Heat gathers at the center, and the core grows steadily warmer. At this stage, the object is not yet a true star, but a protostar, a dim ember glowing softly from the energy of its own contraction. Millions of years pass before the core reaches a remarkable threshold, between 10 and 18 million degrees Celsius. Only then does a true miracle of physics unfold. Hydrogen nuclei, moving with extraordinary speed, overcome their natural repulsion and fuse together. Helium is formed, and in that instant, an immense release of energy floods outward as light. A star has awakened. Energy briefly triumphs over gravity's crushing grip, and a new beacon shines into the surrounding darkness. Once born, a star is no longer merely gas. It becomes a living structure of plasma, the fourth state of matter. At such extreme temperatures, electrons are stripped from atomic nuclei, creating a restless sea of charged particles. This is where nearly all ordinary matter in the universe exists. In luminous, electrified motion, a stable star is a delicate balance, a continuous negotiation between two opposing forces. Gravity pulls inward without mercy, while nuclear fusion pushes outward with equal resolve. Should fusion ever falter, gravity would claim its victory in an instant. Within each star lies a layered architecture of quiet complexity. At the core, where matter is compressed to a density far greater than water, energy is born. Surrounding it is the radiative zone, where light struggles to escape, absorbed, released, and redirected countless times. A single photon may wander for tens of thousands, even hundreds of thousands of years before reaching freedom. Beyond this lies the convective zone, where hot plasma rises and cool plasma sinks, like a slow, cosmic boil. Finally, light emerges from the photosphere and begins its long journey across space, carrying with it the silent announcement of the star's existence. Yet in the stellar realm, mass writes destiny. A star's initial weight determines its color, its brilliance, its lifespan, and its final farewell. Small red dwarf stars are the universe's quiet survivors. Cool and efficient, they burn their fuel with great patience and may shine for trillions of years, far longer than the universe has yet existed. At the opposite extreme stand the blue giants, vast, luminous, and extravagant. Their immense gravity forces their cores into furious activity, consuming fuel at an astonishing pace. Though rich in hydrogen, they live fast and briefly, ending their lives in spectacular supernovae, brilliant, violent, and fleeting. Scale, too, defies imagination. Some stars, like white dwarfs, are no larger than Earth. Others, such as Betelgeuse or UY Scuti, are so immense that, placed where our sun now rests, they would engulf the inner planets and stretch toward the orbits of Jupiter or beyond. Their light can dominate entire regions of a galaxy. Yet this grandeur brings fragility. At their surfaces, gravity is weak, and matter is easily swept away by powerful stellar winds, returning once more to space. Stars do far more than adorn the night sky. They are the true architects of the universe. In the aftermath of the Big Bang, creation was simple: hydrogen and helium alone. Inside stellar cores, through relentless nuclear reactions, complexity was born. Carbon, oxygen, nitrogen, the essential elements of life, were forged step by step, heartbeat by heartbeat. When massive stars die, they offer a final act of generosity. In supernova explosions of staggering power, they scatter their precious elements across the cosmos. In those moments, even heavier elements, gold, platinum, uranium, are created. Without these deaths, the universe would remain a thin, lifeless fog. There would be no rocky planets, no oceans, no living bodies. The calcium in your bones, the iron in your blood, the oxygen in every breath, all were born in stars that lived and died long before Earth existed. We are, quite literally, stardust. Within our Milky Way, a graceful spiral of hundreds of billions of stars, this process continues. New stars ignite in the spiral arms, keeping the galaxy alive. Stellar winds and radiant energy regulate future births, while steady stars like our sun create calm sanctuaries where life can take hold and slowly unfold. And now, as images of misty nurseries, glowing plasma, and the endless cycle of matter soften and fade, allow the night to settle around you. You are here, an extraordinary being shaped from ancient stellar ash, breathing air forged in nuclear fire. The starlight you see is not merely light, it is memory, a message sent across vast distances and deep time. Every star above you is a quiet witness to the universe's long history, performing its silent dance with dignity and resolve. Let the whispers from the cosmic frontier ease your thoughts, guiding you gently toward rest. Though the stars may seem distant, their legacy lives on in every beat of your heart, forever linking you to the source of all things. Are you still here, night travelers? If you are awake, let the gentle warmth of this fire settle into your soul. And together, let us listen to an epic poem written not in words, but in light itself. The life cycle of light, from cocoons in darkness to brilliant radiance. There is nothing you need to remember tonight. No numbers to hold on to, no names to memorize. Let your thoughts drift freely, as light as cosmic dust. Let your breathing slow with each sentence, as this story of starlight gently carries you toward rest beneath the eternal glow of the heavens. Prelude. Cocoons in darkness. Every great story in the universe begins not with sound or motion, but with stillness and with darkness. Long before a star ever shines, it exists as a vast silent cloud of dust and gas, wandering the cold spaces between the stars. These regions, known as nebulae, the great nurseries of creation, are made mostly of hydrogen, the simplest and most abundant element the universe has ever known. These immense structures, called giant molecular clouds, can stretch across hundreds of light years, holding masses millions of times greater than our sun. For millions of years, they drift quietly at temperatures barely above absolute zero, around 10 degrees Kelvin. Nothing seems to happen, and yet, within this deep silence, a patient force is at work. Gravity. Gravity moves slowly, but it never forgets. Like a careful builder, it begins to draw particles of dust and gas ever closer together. For a long time, balance holds. But once the cloud grows dense enough, crossing a critical limit known as the Jeans mass, pressure can no longer resist gravity's pull. The cloud yields, and collapse begins. Sometimes this collapse is gently encouraged by distant events, the shock wave of a dying star, or the slow collision of galaxies. And so, the giants begin to fall inward. Bach cocoons, and the birth of a protostar. The collapsing cloud does not form a single body. Instead, it fragments into thousands of smaller knots. Each fragment becomes a dense, opaque cocoon, what astronomers call a Bach globule. Inside these dark cocoons, matter flows steadily toward the center. Motion becomes heat. Heat builds quietly, relentlessly. At the heart of each cocoon, a warm sphere takes shape, a protostar. It glows faintly, not yet powered by fusion, but by gravity itself. It is not fully alive, but it is no longer dormant. Like an unborn child cradled in the womb of the universe, it feeds from the surrounding disk of matter, growing slowly, patiently. The miracle of nuclear fusion. The long night finally begins to lift when the temperature in the protostar's core reaches an extraordinary threshold, between 10 and 18 million degrees Celsius. At this point, hydrogen nuclei move so violently that they overcome their natural repulsion and fuse together, forming helium. In this moment, one of nature's deepest miracles occurs. Nuclear fusion begins. Matter is transformed into energy, released as heat and light, exactly as described by Einstein's quiet equation, E equals mc squared. When this process stabilizes, the outward pressure from fusion perfectly balances the inward pull of gravity. The struggle pauses, harmony is achieved. A star is born. Light replaces darkness, and the universe gains another voice in its vast, luminous choir. The brilliant halo, life on the main sequence. With its awakening complete, the star enters the longest chapter of its life, the main sequence. Here, it will spend nearly 90% of its existence calmly converting hydrogen into helium. This phase is defined by an eternal tension. Gravity presses inward without rest, while the energy from fusion pushes outward in constant reply. Imagine a climber hanging from a cliff. Gravity pulls him down, while his muscles strain to keep him alive. As long as strength matches pull, balance endures. Our sun is a perfect example of this mature stage. A modest, middle-aged star, it has shone steadily for about 4.6 billion years, quietly sustaining life without drama. The sun is not solid, but a vast sphere of plasma, the fourth state of matter. Its structure unfolds in layers of quiet wonder. The core, where matter is 150 times denser than water and temperatures reach nearly 16 million Kelvin. The heart that powers the entire solar system. The radiative zone, where light struggles outward, taking tens of thousands of years to escape. The convective zone, where hot plasma rises and falls like boiling water. The photosphere, the visible surface, where light finally begins its long journey through space. Each second, the sun converts hundreds of billions of kilograms of hydrogen into helium, turning 4 billion kilograms of matter directly into energy. This steady fire warms our planet, shapes our climate, and quietly sustains every breath we take. Mass is destiny. Not all stars live the same life. In the universe, mass is destiny. Massive stars burn fast and bright. Their immense pressure drives fusion at a furious pace, granting them lives that last only a few million years. They shine brilliantly, and then they are gone. Small red dwarf stars, by contrast, are patient and frugal. They sip their fuel so slowly that they may shine for trillions of years. None born so far has ever truly died. They glow quietly, like enduring embers in the cosmic dark. The collapse and the legacy. No star, however steady, shines forever. When hydrogen in the core is exhausted, balance is lost. For stars like our sun, this leads to expansion into a red giant, swelling enough to consume the inner planets. Eventually, its outer layers drift away, forming a glowing planetary nebula, while the core remains as a white dwarf, dense, silent, slowly cooling through deep time. Massive stars meet a more violent end. When fusion creates iron, an element that yields no energy, collapse comes suddenly. The star implodes, then explodes as a supernova, scattering newly forged elements across space. What remains may be a neutron star, unimaginably dense, or a black hole, where gravity claims final victory and even light cannot escape. We are stardust, and yet no star dies in vain. Every atom of calcium in your bones, every atom of iron in your blood, every breath of oxygen you take was once forged in the heart of a star. We are not merely observers of the universe, we are its legacy. Now, as this long story of light and darkness gently fades, feel the quiet of the night return. You are here, a being shaped by ancient stars, resting beneath their distant glow. The light you see overhead is not just illumination, but memory itself, traveling across time to reach you. Let those distant whispers calm your thoughts. Let them remind you that you belong to something vast, patient, and enduring. Our story begins in the deep stillness of the darkest regions of space, within immense clouds of dust and hydrogen gas known as nebulae. In these silent realms, gravity, the universe's most patient and tireless architect, begins its quiet work, gathering tiny grains of matter together. As a cloud slowly contracts under its own weight, it starts to warm and rotate, giving birth to a glowing embryo known as a protostar. Yet a star does not truly awaken until a critical moment arrives, when pressure and temperature at its core rise high enough to ignite nuclear fusion. Hydrogen atoms merge into helium, and an enormous flood of energy is released. Light is born, and darkness recedes. At this very instant of birth, a silent verdict is already written for the star. That verdict is determined not by its color, nor by its place in the galaxy, but by one simple factor: the amount of mass it gathered from the primordial cloud. In the stellar universe, mass is destiny. It is the unseen hand that guides a star along its entire life path. Mass creates gravity, and gravity is relentless. It constantly tries to crush the star inward, toward its core. To survive, the star must respond with equal force, generating outward pressure through nuclear reactions, holding gravity at bay. This eternal struggle between collapse and resistance is the quiet engine behind all stellar diversity. Let us first consider the smallest and most enduring stars, the red dwarfs. These are the universe's silent timekeepers. With masses ranging from only about 8 to 50% of our sun, they are by far the most common stars, making up as much as 75% of all stars in the Milky Way. Their modest mass means gentler gravity at the core, lower temperatures, and fusion reactions that proceed slowly and efficiently. Inside a red dwarf, nature practices perfect economy. Unlike the sun, which is divided into distinct layers, a red dwarf is fully convective. Hydrogen from the outer regions is continuously mixed down into the core, while helium produced by fusion is carried back outward. Almost every atom of fuel is eventually used. This remarkable efficiency grants red dwarfs an almost unimaginable lifespan. They can shine steadily for tens of billions, even trillions of years. Considering that the universe itself is only about 13.8 billion years old, this means that every red dwarf ever born is still shining today. None have yet lived long enough to die. They are the universe's quiet witnesses, small, persistent flames that will outlast even the grandest suns. When a red dwarf finally exhausts its fuel, far in the distant future, it will not erupt or collapse violently. It will simply fade, shrinking into a cool white dwarf made mostly of helium, slowly surrendering its warmth to the dark. Standing in sharp contrast are the massive stars, the flamboyant giants of the cosmos. With masses at least 8 times that of the sun, and sometimes exceeding 100 times more, these stars live fast and shine fiercely. If red dwarfs are patient walkers on a long road, massive stars are sprinters, burning all their energy in a breathtaking dash. Their immense mass creates crushing gravity, forcing the core to reach extreme temperatures and pressures. As a result, nuclear fusion runs at a frantic pace. Paradoxically, the stars with the greatest reserves of fuel are the ones that consume it the fastest. Massive stars burn hydrogen millions of times more rapidly than the sun, granting them lifespans of only a few million years, a fleeting moment in cosmic time. These giants shine with blue or bluish-white light, revealing surface temperatures that can soar to tens of thousands of degrees. Their brilliance is so intense that powerful stellar winds strip away their outer layers, casting matter into space long before death arrives. Near the end, a massive star's interior resembles a layered onion. Hydrogen burns in the outer shells, helium beneath it, followed by carbon, neon, oxygen, and silicon, each layer feeding the next. At the center, iron accumulates, and iron is the point of no return. Iron is the final sentence written in a massive star's fate. While the fusion of lighter elements releases energy, iron consumes it. Once an iron core forms, the outward pressure vanishes. Gravity wins instantly. The core collapses at unimaginable speed, rebounds, and the star detonates in a catastrophic supernova. For a brief moment, a single dying star can outshine an entire galaxy. To understand this difference in destiny, imagine 2 gamblers at a cosmic table. A red dwarf bets cautiously, placing tiny wagers and playing indefinitely. A massive star arrives with a vast fortune, but wagers recklessly, burning through its wealth in a few dazzling rounds. Mass is the stake, and fusion is the rhythm of the game. The final act of massive stars is their greatest gift. After the supernova fades, what remains may be a neutron star, so dense that a teaspoon of its matter would weigh as much as a mountain, or a black hole, where gravity reigns absolutely and even light cannot escape. Yet their violent deaths are not in vain. In the furnace of collapse and explosion, heavy elements such as gold, platinum, and uranium are forged and scattered across space. These atoms seed future stars, planets, and life itself. Every living being on this quiet blue planet is part of that legacy. The iron in your blood, the calcium in your bones, the oxygen filling your lungs, all were born in the hearts of massive stars that lived and died billions of years ago. Had the universe been filled only with long-lived red dwarfs, rich in endurance but poor in chemistry, life as we know it would never have emerged. And now, as this story of gravity, fire, and fate gently fades, let the whispers from the cosmic frontier calm your thoughts. Though the stars may lie far beyond reach, their legacy pulses within you, quietly and steadily, with every beat of your heart. Now, let us turn our gaze to the strangest beings of all, the remnants of stars that have already burned out, yet continue to exist as quiet defiance against the familiar laws of physics. Retired stars and the last glow, white dwarfs. Our journey begins with the fate awaiting stars like our own sun. When a star of moderate mass exhausts its hydrogen fuel, it does not simply disappear into the darkness. Instead, it gently sheds its outer layers, releasing them into space, and leaves behind a hot, compact core known as a white dwarf. I often think of white dwarfs as retired stars. Their blazing youth has passed. What we see now is merely the lingering warmth of a long and productive life. They no longer generate energy through fusion. Every photon they emit is borrowed from the past. White dwarfs are among the strangest objects in the cosmos. Imagine compressing the entire mass of the sun into a sphere no larger than Earth. In such a state, matter reaches densities beyond ordinary comprehension. A single teaspoon of white dwarf material would weigh several tons on Earth. Here, atoms are pressed so tightly together that their electron shells collide, producing a powerful resistance known as electron degeneracy pressure. It is this quiet quantum force that holds the star up against gravity's relentless pull. One of the most famous examples is Sirius B, the faint companion to the brilliant Sirius, shining softly, like a final ember, reminding us of the inevitable fate of average stars. Eternal silence in the darkness. Black dwarfs. Over spans of time so vast they strain the imagination. Billions, even trillions of years, white dwarfs will slowly cool. Their stored heat will leak away, little by little, until they no longer glow at all. At that distant stage, they become what we call black dwarfs, cold, dark bodies that emit neither light nor warmth. And yet, there is something profoundly poetic here. There are no black dwarfs in the universe today. Our cosmos, at 13.8 billion years old, is still too young. Not a single white dwarf has had enough time to cool completely. Black dwarfs belong to the far future, an era when galaxies grow quiet and the Milky Way itself fades into darkness. They are the silent echoes of once brilliant symphonies, waiting patiently at the very edge of time. The monsters of density, neutron stars. If white dwarfs represent a peaceful retirement, then neutron stars are born from catastrophe. When a massive star ends its life in a supernova, the violence is unimaginable. The stellar core collapses with such ferocity that even the resistance holding up a white dwarf is overwhelmed. Gravity forces electrons to merge with protons, forming neutrons. The result is a neutron star, a sphere only about 20 kilometers wide, roughly the size of a small city, yet containing more mass than the sun. Its density defies intuition. A matchbox of neutron star material would weigh billions of tons, comparable to an entire mountain compressed into the palm of your hand. Their surfaces are solid, their gravity crushing beyond endurance. These are remnants forged in iron and fire, where familiar physics begins to fracture, and matter exists in forms unseen anywhere else in nature. Lighthouses of the void, pulsars. Among neutron stars, some take on an even stranger role. These are pulsars. As a star's core collapses from a vast sphere into something scarcely larger than a city, its rotation accelerates dramatically. Pulsars spin at astonishing speeds, sometimes hundreds of times per second, emitting narrow beams of radiation from their magnetic poles. As these beams sweep across space, they flash past Earth with clock-like precision, much like cosmic lighthouses. Their timing is so exact that when pulsars were first discovered in the late 1960s, scientists briefly wondered whether they were artificial signals. They are not messages from distant civilizations, but they are something equally remarkable. The most precise natural clocks in the universe, spinning steadily in the dark, marking time long after their parent stars have vanished. The magnetars of death. Magnetars. Perhaps the most extreme members of the neutron star family are magnetars. These stars possess the strongest magnetic fields known, trillions of times more powerful than Earth's. Their magnetic force is so intense that it can distort atomic structures and tear apart molecules from thousands of kilometers away. When this immense magnetic field shifts, it triggers violent starquakes, releasing more energy in a fraction of a second than the sun emits over hundreds of thousands of years. Magnetars are nature's most unforgiving laboratories, places where matter is tortured by invisible forces beyond human experience, solitary, dangerous, and profoundly alien, hybrid souls and hypothetical entities. Beyond even these extremes, science dares to imagine stranger possibilities still. There may exist quark stars, where pressure becomes so intense that neutrons themselves break apart into their fundamental components, or exotic structures like Thorne-Zhitkov objects, in which a neutron star becomes embedded within a red giant, creating a star within a star. Though still theoretical, such ideas remind us that the universe is never finished surprising us. There is always room for forms of existence that refuse to follow familiar patterns. The absolute triumph of darkness. Black holes. Our journey ends where gravity achieves total dominance, with black holes. When a truly massive star collapses, no known force can halt the descent. The core shrinks into a point of infinite density called a singularity, wrapped inside an invisible boundary known as the event horizon. Black holes are not cosmic vacuum cleaners, but regions where space and time are warped so profoundly that escape becomes impossible. Even light is held prisoner. At the heart of our Milky Way, Sagittarius, a star rests in silence, a black hole 4 million times the mass of the sun, quietly guiding the motion of billions of stars. When a star wanders too close, gravity stretches it into a long, luminous thread in a final cosmic dance before drawing it beyond the horizon forever. And now, as the night deepens, let these remnants of lost stars drift through your thoughts. They are not symbols of endings, but of transformation, reminders that even after light fades, existence continues in quieter, stranger forms. Night travelers, you have already encountered the gentle spirits of the stars. Now, stay with us a little longer as we step into a quiet yet dramatic arena, the great showdown between the tiniest sparks and the grandest giants, where the universe reveals its most striking contrasts. The sun, the measure of great ordinariness. Every contest needs a familiar point of reference. For us, that measure is the sun, the calm golden star ruling the center of our solar home. The sun is a vast sphere of glowing plasma, where nuclear fusion steadily transforms hydrogen into helium, second after second, releasing the energy that warms Earth and sustains life. To our human senses, it feels immense. It contains 99.86% of the total mass of the entire solar system, with a diameter of about 1.4 million kilometers, making it 109 times wider than Earth. If the planets were small marbles, more than 1 million Earths could rest inside the Sun. And yet, when placed on the grand map of the Milky Way, the Sun becomes something far more modest. It is classified as a G2V main sequence star, often called a yellow dwarf. At 4.6 billion years old, it is in a stable middle age, expected to shine gently for another 5 billion years. It is brighter than most stars in our galaxy, about 85% brighter, but compared to the true extremes of tonight's story, the Sun becomes a quiet reference point, a single grain of sand in a cosmic desert. Tiny contestants, the enduring power of faint sparks. Now, let your thoughts drift away from that familiar glow into the dimmer regions of space where the smallest contestants reign. Here we find the red dwarfs, the most patient and economical stars in the universe. These stars possess only about 1/10 the mass of the Sun, with surfaces thousands of degrees cooler. Among them is 2MASSJ 0523-1403, one of the smallest stars ever discovered, weighing only about 80 times the mass of Jupiter, just enough to ignite fusion. Any lighter, and it would have failed to become a star at all, lingering forever as a brown dwarf. Do not let their faint red light mislead you. In the quiet contest of endurance, red dwarfs are unmatched. Their small mass creates gentler gravity at their cores, allowing hydrogen fuel to burn at an extraordinarily slow and efficient pace. While the Sun's life spans roughly 10 billion years, a red dwarf can shine steadily for trillions of years, far exceeding the current age of the universe. Long after galaxies grow dim and brilliant giants have vanished, these tiny sparks will still glow softly. Silent keepers of time, witnesses to epochs yet unborn. Giant adversaries, an epic of fire and agony. Standing in stark contrast are the supergiants and hypergiants, the true titans of the cosmos. Consider UY Scuti or Stephenson 2-18, the largest star currently known. Stephenson 2-18 possesses a radius roughly 2,150 times that of the Sun. If placed at the center of our solar system, its surface would swallow Earth, pass beyond Jupiter, and stretch toward Saturn's orbit. Its sheer volume is so immense that 10 billion suns could fit within it. To circle this star's equator, light itself would need 8.5 hours, the same time it takes light to travel from the Sun to Pluto at its most distant point. Another towering presence is WOHG 64, a red supergiant in the Large Magellanic Cloud, 160,000 light-years away. Wrapped in a thick veil of dust, it shines hundreds of thousands of times brighter than the Sun, shedding its outer layers into space, forming vast clouds of glowing cosmic dust. Yet greatness carries a heavy cost. These giants live brief, intense lives. Their enormous mass generates crushing gravitational pressure, forcing their cores to burn hydrogen at a frantic pace. To avoid collapse, they consume their fuel millions of times faster than the Sun, limiting their lives to only a few million years, a fleeting moment on the galactic clock. The extreme contrast, when destiny is written in weight. This silent showdown reveals a fundamental truth of the universe: mass is destiny. In size, if the Sun were a tennis ball, the red dwarf 2MASSJ 0523-1403 would be no larger than a pea, while Stephenson 2-18 would rise like a 50-story building. In brightness, giants such as Eta Carinae can shine millions of times brighter than the Sun, releasing in seconds what our Sun produces over thousands of years. A red dwarf, by contrast, may remain invisible to the naked eye, even if it drifts near our solar neighborhood. In lifespan, here lies the great paradox. The smallest stars endure through patience, lasting trillions of years. The giants burn with overwhelming brilliance, sacrificing longevity for spectacle. In the end, the giants depart in thunder, exploding as supernovae or hypernovae, scattering heavy elements that seed new stars, planets, and life itself. The smallest stars fade quietly, cooling into white dwarfs, and far in the future, slipping gently into darkness as black dwarfs. Every great story in this universe is born in stillness and darkness. In those silent depths, vast, giant molecular clouds drift through interstellar space like cold, forgotten ghosts. For millions of years, they move almost without motion, resting at temperatures barely above absolute zero, around 10 Kelvin, harboring the most ancient ingredients of creation, hydrogen above all else, a trace of helium, and fine grains of cosmic dust. And then, quietly, patiently, a force begins its work. Gravity. Like an architect who never hurries, gravity gently draws dust and gas closer together, tightening its invisible grip, forming a slow and irreversible spiral. When a region of the cloud becomes dense enough, crossing a critical threshold known as the Jeans mass, balance is lost. The cloud yields to its own weight, collapsing and fragmenting into thousands of smaller knots, each one a silent promise of a future sun. Within these dense cocoons, known to astronomers as Bach globules, matter falls inward, freely and relentlessly. Motion turns into heat. The core grows warmer, brighter. Yet this is not a true star. Not yet. It is a protostar, glowing faintly, sustained only by the energy of gravitational contraction. Millions of years pass. Pressure builds. Temperature rises. And then, at last, the threshold is crossed. 10 to 18 million degrees Celsius. A quiet miracle unfolds. Hydrogen nuclei move so fast that they overcome their natural repulsion and fuse together, forming helium. In that instant, nuclear fusion begins, releasing a tremendous flood of energy as light. A star is truly born. For the first time, outward energy pushes back against gravity's crushing pull. Darkness retreats. Space is illuminated. When a star awakens, it is no simple ball of gas. It becomes a plasma being, matter in its fourth and most dynamic state. At such extreme temperatures, electrons are stripped from atoms, creating a glowing sea of charged particles, ions and free electrons, moving in restless harmony. This is where 99.9% of the universe's ordinary matter resides. A living star is a masterpiece of balance. Fusion in the core pushes outward with fierce pressure, while gravity pulls inward without mercy. From this tension comes stability. From stability, light. Inside, the star reveals a layered structure, like a carefully written map. At the core, where matter is 150 times denser than water, energy is forged without pause. Surrounding it lies the radiative zone, where photons stumble endlessly, absorbed, re-emitted, redirected, sometimes taking tens of thousands of years to escape. Only then does light finally break free from the photosphere, beginning its long journey across space, carrying word of the star's existence to distant eyes. Yet in the stellar world, one truth governs all others. Mass is destiny. A star's initial weight determines everything: its color, its brightness, its lifespan, and the manner of its death. The smallest stars, red dwarfs, are the most enduring. Cool, modest, and efficient, they sip their fuel slowly, capable of shining for trillions of years, far longer than the universe has existed so far. At the other extreme stand the blue giants, brilliant, massive, and impatient. Their immense gravity forces their cores into furious fusion, burning fuel millions of times faster than the sun. Though rich in hydrogen, they squander it quickly, living only a few million years before ending in catastrophic supernovae. They burn brightly, briefly, and vanish. Stars of spectacle and sacrifice. Size, too, defies imagination. While white dwarfs shrink to the scale of Earth, supergiants like WOHG 64 or Stevenson 2-18 grow so vast that, if placed where our sun resides, they would engulf every rocky planet and stretch toward Saturn's orbit. Their brilliance can light entire regions of a galaxy, yet their enormous size leaves them fragile, their weak surface gravity allowing stellar winds to peel matter away continuously into space. Beyond these lives lie stranger remnants, the quiet souls after the flame. Neutron stars, born from collapsed supernova cores, compress more mass than the sun into a sphere no wider than a city. Their density is beyond intuition. A teaspoon of their matter would weigh billions of tons. Some spin hundreds of times per second, becoming pulsars, cosmic lighthouses sweeping space with precise beams of radiation. Others evolve into magnetars, whose magnetic fields are so powerful they can disrupt atomic structures from thousands of kilometers away. And finally, at the edge of understanding, stand black holes. When the most massive stars collapse, gravity wins completely, compressing matter into a singularity where space and time themselves bend beyond recognition. Even light cannot escape. At the heart of our Milky Way, Sagittarius, a star, 4 million times the mass of the Sun, silently governs the motion of billions of stars. These are not merely destroyers. They are cosmic regulators, shaping galaxies, triggering creation even as they consume. Stars do far more than light the night. They are the architects of existence. After the Big Bang, the universe held only hydrogen and helium. Inside stellar cores, through relentless fusion, heavier elements were born: carbon, oxygen, nitrogen, the essential building blocks of life. And when massive stars died, they scattered these atoms into space, seeding planets, oceans, and living bodies. Every calcium atom in your bones, every iron atom in your blood, every breath of oxygen you draw was forged in a star that lived and died billions of years ago. We are not visitors to the universe. We are stardust remembering itself. Now, as images of misty nebulae and glowing plasma slowly fade, allow the night to settle around you. You are here, safe on Earth, held gently within the universe's quiet embrace. The starlight reaching your eyes tonight is not merely light, it is history, traveling across time to find you. Each star is a witness, moving in silent dignity through the dark. Imagine yourself as a small ray of light, drifting back into that vast velvety ocean, wrapped in a halo of distant suns. They did not build this universe merely to exist, but to create a place where consciousness could arise and look back in wonder. Let the whispers of the cosmos calm your thoughts. However distant the stars may be, their legacy pulses within you, steady as your heartbeat. The universe beyond is immense and mysterious, yet it is also home, lit by billions of quiet suns, each recounting the long, patient epic of life. Take a slow, deep breath. Let your chest gently rise and feel the quiet relief spreading through your body as the weight of a long, weary day slowly loosens its grip. Imagine yourself resting on an invisible boat of thought, drifting across a velvety ocean of space where the soft glow of distant stars weaves an endless tapestry of existence. Tonight, we will not simply look up at the sky as we so often do. Together, we will journey backward through time to rediscover how our ancestors once gazed upward and allowed the stars to illuminate their inner world. Prelude: the light within the human soul. For millions of years, long before the glare of city lights or the flicker of electronic screens, night descended upon the earth in complete and unbroken darkness. In that profound blackness, our ancestors lifted their eyes and found a kingdom that never faded: the stars. To them, These were not lifeless points of light. They were living presences, divine beings, and the only map by which humanity could locate itself within an immense and mysterious universe. From the very dawn of civilization, the stars have been inseparable from human culture. Early observers noticed a distinction between the fixed stars, which held steady positions in the sky, and the wandering stars, which the Greeks later called planetae, the planets, objects that slowly traced their paths through the constellations. Across nearly all ancient civilizations, these celestial wanderers were believed to be gods, endowed with supreme power and influence over earthly fate. In ancient Mesopotamia, the Babylonians bestowed the names of their deities upon the planets: Ishtar for Venus, Nergal for Mars, Marduk for Jupiter. These names were not poetic flourishes. They reflected a deep conviction that the heavens governed the destinies of nations and individuals alike. In Greece, the planets mirrored the gods of Olympus: swift Hermes linked to Mercury, radiant Aphrodite to Venus. Even the sun itself, our nearest star, was revered across cultures as Ra in Egypt, Surya in India, and Helios in Greece, each embodying life, power, and renewal. Yet the influence of the stars reached far beyond belief and worship. They were practical guides, essential to survival. By tracking the sun's movement against the stars and the horizon, early societies created calendars to govern agriculture. In Egypt, the dawn rising of Sirius alongside the sun foretold the annual flooding of the Nile, the single lifeline of the land. Even the Milky Way, that vast river of light arcing across the sky, held sacred meaning. In India, it became the Ganges of the sky, while in East Asia, it was seen as a luminous silver river spanning the heavens. The first pages of history, written in light. Humanity's true journey toward understanding the stars began when reverence gave way to careful observation and systematic record-keeping. Some of the earliest known star maps appeared remarkably early, including an Egyptian star chart, precisely dated to 1534 BC. Yet it was the Babylonian astronomers, toward the end of the second millennium BC, who pioneered the scientific cataloging of the sky. They developed functional models of planetary motion and recorded the movements of the sun and moon in texts such as Emul Apin. While deeply intertwined with astrology, these works quietly laid the groundwork for later exact sciences. The Babylonians identified Mercury, Venus, Mars, Jupiter, and Saturn, the only planets visible before the invention of the telescope, and followed their paths with remarkable precision. In ancient Greece, astronomy shifted from arithmetic patterns to geometric reasoning. Aristotle compiled one of the earliest star catalogs around 300 BC. In the 2nd century BC, Hipparchus expanded this effort, listing 1,020 stars. Centuries later, Ptolemy's Almagest became the definitive astronomical text for more than 1,000 years. Within its geocentric framework, 7 celestial bodies, including the sun and moon, were classified as planets, all believed to circle the Earth according to elegant but complex laws. Parallel to this Western tradition, Chinese astronomy developed with equal sophistication. While many cultures believed the heavens were eternal and unchanging, Chinese astronomers understood that the sky could transform. In the year 185 AD, they recorded the first known observation of a supernova. Another such explosion, in 1054, the event that created the Crab Nebula, was carefully noted by both Chinese and Islamic scholars, revealing a long-standing commitment to monitoring the living sky. During the Middle Ages, Islamic astronomers inherited and refined Greek knowledge with extraordinary dedication. They preserved ancient texts, expanded mathematical techniques, and founded large observatories. Many star names still spoken today, Betelgeuse, Aldebaran, carry their Arabic origins. In 964, Abd al-Rahman al-Sufi published the Book of Fixed Stars, documenting distant star clusters and even the Andromeda Galaxy. A century later, Al-Biruni described the Milky Way as a multitude of faint nebula-like stars, an astonishing insight for his time. Human curiosity continued to push outward. In 1584, Giordano Bruno dared to suggest that the stars were suns like our own, possibly surrounded by other worlds, perhaps even other Earths. Though fiercely opposed in his era, this idea quietly shifted humanity's place in the cosmos. Newton would later confirm that the same laws governing a falling apple also rule the motion of the heavens. Are you still with me, night travelers? If sleep has already found you, that is a gentle victory. If not, let the warmth of this quiet fire continue to soothe your thoughts. Together, we will begin with Galileo's simple telescope, pass through the hidden language of light revealed by spectroscopy, and eventually arrive at the electronic eyes drifting silently through space, gazing back toward the dawn of the universe. There is no need to remember equations or numbers. Let your mind grow light, like cosmic dust, as your breathing slows and the story carries you toward rest, beneath the timeless halo of the stars. Galileo's telescope. The moment. Our perspective changed. The great transformation began on a winter night in 1610, when an Italian scholar named Galileo Galilei lifted a modest instrument toward the sky. He aimed his telescope at a faint white band stretching across the darkness, the Milky Way. For thousands of years, this glowing arc had been explained as mist, or myth, or an atmospheric illusion. Even Aristotle believed it to be a phenomenon of Earth's air. But through Galileo's lens, the illusion dissolved. That soft, milky glow fractured into countless individual stars, so faint, so numerous, that no unaided eye could ever detect them. This was more than a discovery. It was a revolution of perception. Humanity learned for the first time that the universe extended far beyond what vision alone could reveal. The sky was not a painted ceiling, but a deep ocean filled with unseen worlds. Galileo showed that the fixed points of light were not divine decorations, but real, physical objects. With that realization, the Earth-centered universe began to crumble. A new cosmic perspective quietly took shape. In the centuries that followed, the race to understand our galactic home accelerated. In the late 18th century, William Herschel systematically counted stars in 600 different directions, discovering that their density increased toward the Milky Way's core. For the first time, humanity glimpsed the rough structure of its galaxy. In 1845, Lord Rosse constructed the giant telescope known as the Leviathan, revealing spiral shapes within distant nebulae and opening the door to the idea of entire island universes beyond our own. Each improvement in the telescope carried humanity one step farther from myth and one step closer to understanding. With every lens polished and every mirror widened, the boundaries of reality expanded, and the silent language of the stars began, at last, to speak. Reading the code of light, spectroscopy, and the fingerprints of the stars. As night gently settles in, imagine starlight not as simple white points scattered across the sky, but as letters written in a delicate, color-coded script, an ancient language waiting to be read. In the 19th century, a profound breakthrough transformed our understanding of the stars, the birth of spectroscopy. If Galileo's telescope revealed that stars exist, then spectroscopy revealed what they truly are. Pioneers such as Joseph von Fraunhofer and Angelo Secchi discovered that when the light of a star, like our own sun, passes through a prism, it does more than form a smooth rainbow. Embedded within that spectrum are fine, mysterious dark lines. These lines are not imperfections. They are chemical signatures, the unmistakable fingerprints of elements. Each star becomes a musician, each spectrum a melody. By reading these notes, the spectral lines, we learn whether a star's heart contains iron, calcium, magnesium, or other elements forged in cosmic fire. In the early 20th century, Annie Jump Cannon refined this understanding by developing a classification system based on spectral lines, arranging stars from the hottest, type O, to the coolest, type M. Yet the most transformative insight came in 1925 through the work of Cecilia Payne-Gaposchkin. She revealed a truth that initially stunned the scientific world. Despite their differences in brightness and color, stars are composed almost entirely of the two lightest elements, hydrogen, making up roughly 71 to 75%, and helium, about 24 to 28%. With this realization, chemistry became a kind of time machine. Through spectroscopy, we can estimate a star's age by measuring its metallicity, the abundance of elements heavier than helium. The oldest stars, formed soon after the Big Bang, are poor in metals. Younger stars, like our Sun, are enriched with heavier elements created in earlier generations of stellar lives and deaths. Spectroscopy is no longer merely a method of observation. It is a quiet revelation that the calcium in our bones and the iron in our blood were once forged inside the glowing furnaces that adorn the night sky. Modern eyes in the sky, seeing the ends of time and space. Now let your thoughts drift forward to the present, where humanity has lifted its gaze beyond the Earth itself, placing electronic eyes into the vacuum of space. Ground-based observation has always been limited by the atmosphere, a restless veil that absorbs and distorts starlight. To overcome this, we sent our instruments above it, opening a new era of clarity. In 1990, the Hubble Space Telescope was launched, becoming our window into deep time. Its beginning was troubled by a flawed mirror, but a daring repair mission in 1993 transformed it into one of the most powerful scientific tools ever built. Hubble's deep field images revealed thousands of ancient galaxies in regions once thought empty, quietly demonstrating the staggering richness and depth of the universe. Following this path, the European Space Agency's Gaia mission has revolutionized our understanding of distance and motion. With extraordinary precision, Gaia has mapped the three-dimensional positions of more than 2 billion stars in the Milky Way, tracking their subtle movements across time. Through Gaia, we learned that our galaxy is not a fixed structure, but one that gently sways, shaped by dark matter and by ancient encounters with smaller galaxies. Most recently, a new chapter has begun with the James Webb Space Telescope. Working in the infrared, Webb peers through dense clouds of cosmic dust that once concealed the birthplaces of stars. It has carried our vision back 13.5 billion years, to a time only a few hundred million years after the Big Bang, revealing the first generation of stars igniting the primordial darkness. We no longer observe the universe with sight alone. Our instruments now listen across the entire electromagnetic spectrum, from the violent flashes of gamma-ray bursts to the steady X-rays emitted by black holes and neutron stars. Each signal returned is another fragment of a larger story, a reminder that we are not separate from this cosmos. We are participants within it, shaped by light, formed from its legacy, and forever connected to the stars that quietly shine above us. Night travelers, you do not need to remember names or numbers tonight. Let your mind become as light as cosmic dust. Let your breathing slow and allow this story, the legacy of light and the quiet greatness of the human intellect, to carry you gently toward rest beneath the eternal glow of the stars. For millions of years, long before electric lights or glowing screens, the night sky was the most magnificent presence our ancestors knew. When darkness fell, the stars ruled their vision completely. To early humans, these lights were not lifeless objects. They were shining kingdoms that never faded, divine watchers over human fate. Imagine standing in the ancient valleys of Mesopotamia, where Babylonian astrologers etched the paths of the wandering stars into clay tablets. Jupiter was Marduk, the supreme god. Venus was Ishtar, the goddess of love. Saturn was Ninurta, the god of agriculture. These names were not chosen at random. They reflected a deep belief that the heavens governed life on Earth, shaping the culture, faith, and identity of entire civilizations. From the very beginning, the stars were woven into human culture. Early observers learned to distinguish the fixed stars, holding their steady places in the sky, from the planets that wandered slowly among them. In ancient Egypt, the brightest star of all, Sirius, was a herald of survival itself. Its rising at dawn announced the coming floods of the Nile, bringing life-giving silt to dry fields. The oldest known star maps, dating back to 1534 BC in Egypt, show that humanity began organizing the heavens remarkably early. Even the Milky Way became a sacred image across cultures. In India, the Ganges of the sky. In East Asia, the Silver River. In Japan, the Heavenly River. These stories, rich with myth, reveal a shared truth. When faced with the vastness of space, the stars became humanity's most faithful spiritual anchor. A profound change came on a cold winter night in 1610, when Galileo Galilei raised his simple telescope toward a pale band of light stretching across the heavens. Until then, even great minds believed the Milky Way was merely vapor or an atmospheric glow. Through Galileo's lens, that soft band dissolved into countless faint stars, far too small for the naked eye to see. In that moment, our understanding changed forever. The Milky Way was not mist, but an immense ocean of suns. Human greatness often begins this way, not with certainty, but with the courage to question what appears familiar. Inspired by Galileo, William Herschel undertook a monumental effort at the end of the 18th century, counting stars in 600 directions across the sky. He discovered that their numbers increased toward the heart of the Milky Way. Though he mistakenly placed the sun at its center, Herschel opened a new chapter, the study of the structure of the universe itself. He also gave us the word asteroid for objects that resemble stars yet move among the planets. In 1838, Friedrich Bessel achieved another quiet revolution by measuring the distance to a star, 61 Cygni, using parallax. The result was humbling. The stars were not close companions in a small dome around Earth, but distant beacons scattered across an immense and almost unimaginable space. Yet perhaps the greatest triumph of human intellect came when we learned to read the hidden language of light itself. Through spectroscopy, pioneers such as Joseph von Fraunhofer and Angelo Secchi discovered that starlight, when passed through a prism, reveals not only color, but fine dark lines, distinctive signatures of chemical elements. In 1925, Cecilia Payne-Gaposchkin uncovered a truth that reshaped astronomy. Despite their many appearances, most stars are composed primarily of hydrogen and helium. With that insight, chemistry became a bridge through time, allowing us to understand the fundamental substance of the cosmos. Our achievement does not end with knowing what stars are made of, but in realizing what they have given us. Stars are the true architects of the universe, vast furnaces where matter is transformed. In their cores, nuclear fusion forges carbon, oxygen, and heavier elements. When massive stars die in supernova explosions, they scatter these elements across space. Every atom of iron in your blood, every trace of calcium in your bones, every breath of oxygen you take was born in stars that ended their lives billions of years ago. We are, quite literally, stardust, the universe reflecting upon itself through conscious eyes. In the 20th and 21st centuries, our view expanded once more with modern eyes placed in space. Launched in 1990, the Hubble Space Telescope opened a window into deep time, revealing images once beyond imagination. The pillars of creation, where stars are born, and distant fields crowded with ancient galaxies. The Gaia mission has mapped more than 2 billion stars, showing that our galaxy is not fixed and still, but alive with motion and change. And most recently, the James Webb Space Telescope has looked back 13.5 billion years, witnessing the first stars lighting the darkness after the Big Bang. Though the stars lie so far away that their light travels for millions of years, they remain close to us in meaning and memory. Distance is no barrier to understanding. It is a measure of the quiet power of the human mind. We have learned to chart a galaxy of hundreds of billions of stars, to discover worlds beyond our own, and to imagine journeys still to come. Though we are small, we have never accepted isolation. We have gathered fragile photons of light and learned to hear the harmony they form. Now, as images of ancient star maps, Galileo's telescope, and distant stellar furnaces fade, rest in the calm of the night. You are here, safe on Earth, beneath the steady warmth of our golden sun. The starlight you see is not merely a point of light, it is a message from the past, a photograph carried across space and time just for you. Each star is a silent witness to the universe's long history, performing its quiet dance with dignity and patience. Let the whispers of the cosmic frontier soothe your spirit, guiding you into deep and peaceful sleep beneath the everlasting radiance of the stars. No matter how distant they may be, their legacy lives within every atom of your being, connecting you to the source of all things. May you sleep gently under the guardianship of starlight. Good night, night travelers.